Okay, good evening everybody. So welcome to this NPTEL course Introduction to Biomaterials. Now this course will have altogether 42 lectures, and this is the first lecture. So first I'll go through briefly the course objectives. At the end of the course, it is expected that the students will be able to understand the fundamental concepts of material science and what is required to apply for biomaterial science. Then second one is that processing and basic material properties of various biocompatible metals, ceramics and polymer based materials. Third one is that biological property evaluation, like what are the typical biological properties that need to be evaluated to understand the potential or application of a given biomaterial. And then finally that processing and properties of some polymer biocomposites. So these are like most recent developments in the field of biomaterials that also will be covered as part of this course. Now this is briefly the course content. So first I'll introduce you to the basic concepts of material science, because the biomaterials field, actually many people from a number of different disciplines like biology, material science, mechanical engineering, they all work together in this area. So it is important first to have the basic concepts of material science. It will be then followed by the salient properties of important material classes, namely the metals, ceramics and polymers. Third one is the property requirement of biomaterials. The fourth one is the concept of biocompatibility. So biocompatibility is the core idea and the core property requirement for the development of biomaterials. Therefore, an in-depth understanding of what is meant broadly by the biocompatibility that needs to be understood. Now essentially this biomaterials means it is at the interface of the biology and material science. So one needs to have sufficient background of the biological cells and tissues, particularly what is the structure of biological cells, and then essentially I'll also be dealing with at some stage the structure of the protein molecules, collagens and hard tissue, soft tissue and so on. And then what is the properties? Properties means I am talking about mostly the physical properties and mechanical properties. So among these first 5 points, that biocompatibility is extremely important. So I would like to put more stress on this biocompatibility. Then comes the cell material interactions and foreign body response. I'll try to deal mostly the theoretical aspects or theoretical understanding of the cell material interaction. That means how a biological cell interacts with a synthetic material, and as well as the foreign body response, like when a synthetic material will be implanted in the human body, what would be the response of the animal or what would be the response of the human being to this implanted material. Then seventh point is that assessment of biocompatibility of biomaterials. That means what are the different ways, like what are the different testing procedures, how these biomaterials need to be evaluated. And the next point is that in vitro biochemical assays. So here I have mentioned some specific in vitro biochemical assays that I'll be dealing as part of this course. That is namely that MTT assay, osteogenic differentiation using ALP and osteocalcin and so on. Now after the in vitro testing, one needs to do the in vivo testing and histocompatibility assessment. So that will be also part of this course. Now genotoxicity. Genotoxicity means when a biomaterial will be implanted inside the human body or any animal, then what would be the influence of the biomaterial eluate on the gene level toxicity, like whether this material will have any influence so that the DNA will be damaged. And if DNA is damaged, then to what extent the DNA will be damaged, what are the mechanisms of this DNA damage, whether once this DNA is damaged, whether this DNA can be repaired by itself, and how long it will take for this repair of the DNA. So all those things will be discussed in this course. Then coming to the materials part, one of my colleague Dr. Balani will be dealing with some important biometallic alloys like titanium based alloys, stainless steels, cobalt chrome moly alloys. So mostly these are used as the load bearing implant materials. Now I'll be dealing some part of the bioactive ceramics like hydroxyapatite based materials, biodesorbable ceramics like tricalcium phosphate and so on. So there will be a lot of emphasis on the processing of hydroxyapatite based materials, because these are the materials which are widely researched in around different research labs in the world. Then synthesis of the biocompatible coatings on structural implant materials like hydroxyapatite coating on titanium or stainless steel, how they can be processed, what are the properties of these hydroxyapatite coatings and so on, that will also be discussed. Now, plasma spraying of the carbon nanotube reinforced hydroxyapatite, that is the specialty of the other colleague Dr. Balani, who will be taking some lectures as part of this course. Now, microsurgeon properties of glass ceramics. These glass ceramics are essentially used as the dental restorative materials. So, these are researched in our group for quite some time now. So, I would like to spend some lectures on these glass ceramic based materials, mostly Macquarie based dental glass ceramics. I will again focus there on both the materials aspect as well as the biological aspect. Mostly materials aspect means how these glass ceramics are prepared by conventional heat treatment as well as spark plasma sintering, and how their properties will vary depending on what is the content of the crystalline ceramic phase in this glass matrix. Now, coming to the next material class that will be dealt in these lectures are the polymer based biocomposites like high density polyethylene based ceramic composites, and lastly we will be dealing with that what are the design concepts for developing new materials for bioimplant applications, like what are the different property requirements and how these properties can be optimized, and how to process the different implant materials with desired combination of both physical as well as the biological properties. Those will be discussed towards the last few lectures. Some books that will be helpful in this biomaterials course. The first one is that by Jonathan Black, who wrote this book in 1999, that is the biological performance of materials, fundamentals of biocompatibility. The second one is that Silver and Christensen, that is biomaterials science and biocompatibility. Third one is that by Buddy Ratner from University of Washington, Seattle. Actually, he along with some of his colleagues wrote a book, this Biomaterials Science and Introduction to Materials in Medicine. This book has been used as textbook for this kind of course in many universities around the world. Molecular Biology of the Cell, so that is by Bruce Alberts, and again it is this book is mostly devoted to the discussion of the molecular biology aspect of the cell structure, the different signaling processes, how this extracellular matrix has been formed. All those things are discussed in details more from biological aspect in this book. And then fifth one, that is the book that we recently edited, that is the Advanced Biomaterials Fundamentals, Processing and Applications. So this has been recently published by John Wiley. Now these are the lecture wise details. So first 2 or 3 lectures I will be mostly dealing with the basic concepts of material science, salient properties of important material classes. Then next 2 lectures will be on property requirement of biomaterials, concept of biocompatibility. Again, I would like to emphasize that concept of biocompatibility is important. So one who needs to do research, on one who needs to really understand that how these biomaterials need to be developed in the laboratory or at the research lab or at the industrial scale production. So first he needs to understand that what is meant by biocompatibility. Then 6th and 7th lecture will be on structure and properties of biological cells and tissues, and there I will also be dealing with the protein structure and so on. Then lecture 8 to 10th will be cell material interactions and foreign body response. Lecture 11th would be on assessment of biocompatibility of biomaterials, like what are the in vitro assays and in vivo assays, that will be covered in the following lectures. Lecture 18 would be on genotoxicity assessment, that is physical damage to DNA by biomaterial eluates. So I will be mostly dealing with the COMET assays, and at the same time I will be discussing our recent research results on the hydroxyapatite based materials, their genotoxicity effect. Lecture 19 to 21 would be on the metallic materials. Similarly, other subsequent lectures will be discussing the recent developments in bioinert, bioactive and bioresorbable ceramics as well as hydroxyapatite. There will be 2 lectures that will be on the biocompatible coatings on the structural implant materials, and then some lectures will be on specifically on the carbon nanotube hydroxyapatite coatings on the titanium based substrate, and last few lectures will be on glass ceramics, biodegradable polymers as well as design concept for developing new materials. Now the question is, what is material science? Material science essentially deals with the structure property relationship for different materials, like how if the structure, that means we are mostly dealing with the microstructure here, like if the structure at the micro scale, if they can be manipulated, how that will influence the properties. That is the core concept of the material science. Now this concept can be successfully applied to understand the behavior or the properties of metals, ceramics, polymers, as well as the composites. Now this is the famous quadrilateral of the material science, about a tetrahedron of material science tetrahedron. So this also appears in the one of the prestigious journal of material science like Acta Materialia. And here at the four corners of the tetrahedron, there are processing, structure, property, as well as performance. Like now if I want to explain it little bit further, if I change the processing here, this processing will definitely change the structure of the materials, the way the processing is, the process parameter is varied. For example, if I change the sintering temperature, or if I change the sintering time, that will definitely will have a direct influence on the microstructure of these materials. Now if the structure is changed, then this structure will definitely influence the properties like hardness, fracture toughness, strength properties. If the materials is completely dense, then it will have a better strength property. If materials is porous, that will have poor elastic modulus, poor strength properties. Now if the material has inferior properties, they will definitely lead to a very poor performance, whether it is structural performance, whether it's a biological performance, and so on. So what I'm trying to say here, that all these properties, processing, structure, property, performance, they are all correlated with each other. Now how the structure can be assessed in a particular material, one of the simplistic way to use that X-ray diffraction. So this X-ray diffraction means like if there are two parallel atomic planes, and if the incoming X-rays are coming here, now they will be diffracted by the atomic planes, and this diffraction based on this what is the angle of diffraction, then you can find out there is a Bragg's law, which is n lambda is equal to 2d sin theta. This n means that is the order of reflection, lambda is the wavelength of the X-ray, d is the interplanar spacings here, what is meant by d here, and theta is the angle that I have explained just now. Now depending on what is the material, what is the composition, all the materials will diffract the X-rays at a characteristic wavelength and at a characteristic angle theta. And once we have a intensity versus 2 theta, that is a plot, then you can find out that depending on whether it is a copper, nickel, or iron, it will have a characteristic peak, and that is the way you can actually find out the presence of different materials or different phases in a microstructure. What are the different microscopy one would use in this material science? First one is the optical microscopy, which essentially uses the simple optical rays or simple light, and this light, because of the large wavelength of this light, the magnification is also limited, like you cannot really go to the very high magnification here. Then comes the electron microscopy, which essentially uses the electron waves, and it has a very small wavelength, which is of the order of 0.003 nanometer, depending on what is the accelerating voltage. And then this electron microscopy, like scanning electron microscope or transmission electron microscope, the way I have mentioned here, they can be conveniently used to reveal the structure at a much more details, like up to 1 lakh or more than 1 lakh magnification. Now scanning electron microscopy is very easy to make the samples, because sample preparation is very similar, like bulk samples can be used. For transmission electron microscope, the samples need to be essentially very thin, and these thin samples essentially required because this should be electron transparent. That is one of the important criteria for the samples to be used in the transmission electron microscope. Okay, now what are the properties that should be required for biomaterials? The first one is the biological properties, and these biological properties mostly means like what are the whether the material is bioactive, bioinert, or biodegradable in the in vitro or in vivo environment. Then comes mechanical properties, like what is the strength. So biological properties is the most important parameter here as far as the biomaterials application is concerned. Now next comes mechanical properties. Here I would like to draw your attention to the fact that mostly in the material science, where the materials are to be used for structural applications, it is the mechanical properties many times which are required to be optimized, or mechanical properties need to be optimized, or better mechanical properties are the criteria that is set for various applications, like you should have very high hardness or high strength. But when it comes to the biomaterials applications, it is not the mechanical properties, but the biological properties must be first evaluated to a satisfactory level. Now, if the biological properties they meet the criteria for the material to be used in the biological applications or in vitro or in vivo environment, then only the other properties will be of relevance, like mechanical properties, chemical properties, or physical properties. So, therefore, biological properties as opposed to mechanical properties that need to be evaluated and that need to be given more importance while evaluating the biomaterials, while evaluating or while developing the biomaterials. Now, this view graph essentially shows that that different body parts of a human being which can be potentially replaced by synthetic materials or biomaterials. So, essentially these synthetic materials, these can be either metals or synthetic metals or ceramics or polymers or their composites, and these materials they can essentially replace either dental, for example dental restorative like glass ceramics I was talking about. So, these dental applications, many of the ear implants like in the ear they use these hydroxyapatite based materials. Now, cranium or the brain surgery, people use some materials which are radio transparent, like some of the polymeric based materials they can be used in the cranial applications. Maxillofacial reconstruction also people use some synthetic materials. Hard valve like carbon polytetrafluoroethylene, that Teflon, they can be used as the artificial hard valve. So, then spine also some load bearing implants can be used. These orthopedic implants like hip joint or knee joint, here a combination of materials need to be used like metal, ceramic, polymer. Like typically in the hip joint the stem are to be made by titanium, the femoral ball can be ceramic like alumina, and then there is the articulating surface which can be made of ultra high molecular polyethylene or high density polyethylene. So, this kind of materials is not a single material that can be used at all parts of the total hip replacement, but a combination of materials that needs to be used. Similarly, for knee joints also people use the cobalt chrome polyalloys or ultra high molecular polyethylene. These are like typically used in this knee joints also. So, this I must here mention that both this knee joint as well as this hip joint, their mechanical properties are also important, but again here I would emphasize that again biological properties first, then mechanical properties the second most important property in these kind of applications. Okay, bone and biomaterials, like what are the typical composition of a bone. So, this one actually shows the macroscopic structure of a typical human bone. Now, you can see it has a very irregular kind of a structure, right. It is a part of a femur, and this left hand side this shows actually that what are the different components which are contained in this bony structure. And what you see here that 65% of the calcium phosphate, that is calcium hydroxyapatite mineral, these are present along with 23% of collagen. Now, this collagen is actually polymeric based materials, mostly protein rich materials. Then you have 2% non collagen type proteins and 10% water. So, essentially what you can say here from this structural point of view, that bone is nothing but bone is equivalent to polymer ceramic composites, and this polymer ceramic composite, it has essentially natural hydroxyapatite, and this hydroxyapatite content is 65%, and then rest of this stuff is that 23% collagen. So, accordingly some amount of research is also being carried out by various research groups on the developing the polymer ceramic composites to mimic the natural bone composition, natural bone structure. Now, this shows that when you implant a biological material or biomaterial, then how this cell material interaction takes place, but this will be discussed in more details in some of the future slides. Now, coming to the cortical bone properties and different materials, this particular table tells you that what are the different properties or combination of properties that one can get with a natural bone. So, first let us focus on the cortical bone, which is a compact bone or compact part of the bone. It is not a cancellous porous bone. So, cortical bone is that mostly the outer shell of any femur or outer shell of a mostly mature bone. Now this mature bond depending on the anatomical location. Now if you see that there is a large variation in the tensile strength, like tensile strength varies from 60 to 160 MPa. Now this large variation in tensile strength essentially is due to the anatomical location, like depending on the anatomical location of this cortical bone in the human body, like whether it is in shoulder or whether it is in thigh or whether it is in hand, depending on what part of the anatomical location that bone you are taking from. So depending on that anatomical location, your cortical bone property also vary. This variation essentially depends on the anatomical location. But largely what you can see, compressive strength property is around 130 to 180 MPa, elastic modulus is around 3 to 80 MPa, GPa, and fracture toughness depending on again anatomical location is around 2 to 12 MPa square root meter. Now I have put a star on this fracture toughness because I want to highlight here that hydroxyapatite, pure 100% hydroxyapatite, which is the most biocompatible and bioactive material among all the materials being investigated or developed till to date, they match most of the properties of the cortical bone, like it has also equally high tensile strength, much better compressive strength property than natural bone, and elastic modulus also can be tuned to some extent by 80 to 140 gigapascal. But however, if you look at this fracture toughness property, this fracture toughness is around 0.6 to 1 MPa square root meter. This does not even meet the lower bound of the fracture toughness of the cortical bone, which is around 2 MPa square root meter. So therefore, you need to improve the fracture toughness of the hydroxyapatite by some means, so that it meets this particular requirement of the cortical bone property of the fracture toughness. The second point, so first point, as you can mention or you can note down, that fracture toughness is important and fracture toughness needs to be improved for this hydroxyapatite in order to meet the lower bound of the cortical bone property. The second point is the elastic modulus. Now this elastic modulus also needs to be tuned for all the synthetic material. This needs to be tuned between this level 3 to 80 gigapascal. Now if the elastic modulus is very high, then what will happen? The material will carry most of the load instead of the natural tissue, which will surround the synthetic material. For example, if you look at the titanium, the elastic modulus is 117, stainless steel it is 200, titanium alloys is around again 110, and alumina is very high, around 400 gigapascal. Now this magnitude of this elastic modulus here clearly shows that pure titanium, pure alumina, if they are used, they really overshoot the cortical bone properties. However, hydroxyapatite, they are kind of at the higher level or higher, near the higher bound of the elastic modulus of the cortical bone. So therefore, this elastic modulus also needs to be judiciously controlled, so that it actually meets the, it is somewhere in between the two bounds of the elastic modulus of the cortical bone, like lower bound as well as in the upper bound of the cortical bone properties. So this is important. Otherwise, this mismatch in elastic modulus, this elastic modulus mismatch can lead to what we call in biological science, that is called aseptic loosening. Aseptic loosening means that material will take most of the load, and as a result, after some time material will be loose and will break their biological contact with the neighboring tissues, and then there will be stress shielding effect. And once this aseptic loosening takes place, then the implant will be failed, and the implant failure leads to revision surgery and the extreme pain of the patient. So we do not want the aseptic loosening to take place in case of the synthetic materials, and that is the reason I am emphasizing on the fact that elastic modulus mismatch needs to be avoided to the maximum extent as much as possible to get a better biomaterial with acceptable property. Now coming to the different materials, as I said that I will be dealing also with that different classes of materials. So essentially all the engineering materials, they can be classified. So these metals, ceramics and polymers, what I call them, these are like primary material classes. Primary material classes means these are the major materials, but they are different in properties, and they have certain advantageous properties, and they also lack in some properties. For example, metals and alloys, they have very high toughness. These toughness properties are very good, but they have a very modest hardness. Like hardness is not very good when compared to ceramic based materials. Now ceramics, they have toughness and strength variability. These are major concerns in case of the ceramics, and they are essentially brittle. So these things needs to be also taken care of, that while developing ceramic based composites. Now when it case of the polymers, polymers have a low density, it has a high flexibility, but it has really lack the high temperature applications. However, this high temperature applications is not relevant for biomaterials applications. Now when it comes to composites, so essentially you can make metals with ceramics, so which we call, if the metal volume percent is more than 50%, we call it MMC, that is metal matrix composites. Now you can call also ceramic matrix composites like ceramic, if the ceramic volume fraction is much more, then it's called ceramic matrix composites. Now if the polymer volume fraction is much more than ceramic, then we can call them PMC, that is the polymer matrix composites. Now essentially all these composites are developed to take advantages, or to take essentially to optimize the good properties of the metals with the good properties of the ceramics, or essentially to combine the advantageous properties of the two materials to develop a better material with better combination of properties. That was the major motivation of developing the composite materials. And I repeat here that metal matrix composites, ceramic matrix composites, and polymer matrix composites, these are like three different classes of composite materials which are developed and studied. This is like little bit more about these three different materials like metals, ceramics, and polymers. Some of the examples are given here like iron, steel, copper, aluminum, brass. Like steel is essentially an alloy of iron and carbon. So this carbon has an interstitial element in the iron, and that alloy is called steel. Similarly, copper, zinc is brass. So these different alloys, different metals, they are traditionally used for various conventional applications. Now some of the ceramics which are biocompatible like alumina, they are also developed for different applications. Polymers like high density polyethylene, or essentially polyethylene based, or PEG, that is the polyether ether ketone, these are like different biocompatible polymers. Now metals, they are strong and they are deformable but not transparent, and these are essentially high density, so they are much heavier. Now ceramics, they have good properties like very high hardness, but this is a concern, like they are very brittle, and they have a good corrosion resistant. Polymers, they are some are transparent, however they are very flexible, deformable, and they have a low strength. So these are like those highlighted parts or those underlined properties, these are somehow relevant to biomaterials applications. Now some of the alloys like biomaterials like titanium 6, aluminum 4V, these are the extremely high toughness like 105 to 120 megapascal square root meter, and most of the ceramics, they have a toughness of less than 10 MPa square root meter. So some of the metals which are used in biological applications, they can have one order of magnitude higher fracture toughness than their competing ceramic based materials. And however, these applications are essentially limited by the moderate hardness and poor wear resistance properties of the metals. Now polymers, now they are essentially composed of mer units or monomers, and they are essentially long chain molecules. They have a very low density and extremely flexible. They have a low friction, and typical polymers which are used in heart valve, for example polytetrafluoroethylene or polystyrene, and these materials are certainly not suitable for very applications which are essentially for very high temperature. Now third important primary class of materials, that is ceramics, it has excellent hardness, much higher hardness than metals, and some of the ceramics are alumina, zirconia, these are like materials which are extremely good for biomedical applications. Now question is that what are ceramics? Ceramics are essentially a compound of metallic and non-metallic materials, non-metallic elements, and where interatomic bonding is primarily predominantly ionic, and they can be oxides, carbides of metallic elements, like oxides means like zirconia or alumina, these are like different oxides, and mechanical properties are usually good, high strength, however they exhibit very nil ductility or very low ductility, and this is a concern for the ceramic based materials. Now to give an example that how the different properties of the ceramics are in respect to different other materials. For example, alumina, this has a density of around close to 4 gram per cc. However, with iron this has a density of 8 gram per cc. That means equal volume of alumina and equal volume of iron, they have almost like half of the weight, right? And this is important for many times implant applications, because if you want to replace the steel material with equal volume of alumina, the patient also will feel much light at this implant, because alumina has a much lower density compared to that of the steel. So that way density also plays an important role in case of the selection of implants. Now coming to the modulus, now as I said that modulus is important because elastic modulus there should not be much mismatch, and alumina zirconia they have a relatively much higher elastic modulus compared to even steel. So this elastic modulus needs to be tuned before any potential applications can be realized. Now coming to the hardness, these ceramics traditionally you can see that they are a very high hardness, more than 10 gigapascal and above, and that is one of the important properties of the ceramics which are largely exploited in different applications. Now the origin of the word ceramic is derived from the word Greek word keramikos, that is burnt stuff, and these ceramics are broadly defined as a class of inorganic non-metallic materials having ionic or covalent bonds and typically processed or used at high temperature. This is like very formal definition of ceramic based materials. So that means that it has a purely inorganic material and it has ionic or covalent bonding, and they are typically used or processed at high temperature. Now ceramics can be broadly classified into traditional ceramics and engineering ceramics, but as per biomedical applications are concerned, we will be mostly dealing with engineering ceramics like alumina and zirconia, where that properties also depend on high quality fine powders and process parameters. Now as I said that we are mostly dealing with by advanced applications, and one of the advanced applications is this artificial bones, and these artificial bones here essentially are shown here, that is for hip joint applications, and as I explained that it is a combination of materials which are used for hip joints. And what are the important properties which are of relevance for ceramics and biomedical applications? That includes high compression strength and high hardness of these materials. It also is a good wear and corrosion properties, and applications it can be used for articulating surface and joint replacements, bone spacers, as well as the dental applications. Disadvantages are that it has a very high processing temperature and they have mechanically brittle behavior. Okay, in next few slides I would like to highlight the importance of biomaterials. Now in this view graph actually I am showing you that market potential for biomaterials per year, and this market potential shows that in the year 2000 the total US healthcare expenditure was around this much several thousands US dollar, and out of this total US healthcare expenditure, I mean in 2001 it was estimated that a quite sizable fraction of the expenditure was for the R&D development, that is for the research and development work for the developing biomaterials, that was also spent. And if you see that US markets, that was in 2002 for medical device, it was quite a good fraction of the total US healthcare expenditure, right? And if you see that US market for biomaterials per se in 2000, it was again some 1/10 or 1/8 part of the total US medical devices. So what I am trying to emphasize here, that if you see the total US healthcare expenditure, that is, and if you see the total US healthcare expenditure for biomaterials, that is quite a good fraction of the total US healthcare expenditure in the year 2000. And the global numbers, like if you talk about that similar expenditure in Asia as well as Africa and so many other, and as well as in Europe. So these numbers are typically 2 to 3 times the US numbers, because this total healthcare expenditure also depends on the living condition as well as the economy of individual nations, and therefore this total global healthcare expenditure as well as that the ratio of the total market for the biomaterials, that will be quite a good fraction of the large amount of expenditure that is required for the healthcare. So from that part, the development or the R&D activity of biomaterials are also equally important. Now this slide shows you that what is the market potential for biomaterials per year. Now if you see that number of devices in US for intraocular lenses is like several thousands, and as well as if you see the knee prosthesis and hip prosthesis, these are numbers in 2002 that was like 250,000 in each, and dental implants is much more in 2000, that is 910,000 dental implants was required. Now these are like materials which are used for the load bearing applications, and these are like different metals and ceramics or polymers. They are largely used for this kind of applications, like which includes the hip, knee prosthesis and dental implants. Now this slide is important, and I would like to spend some time on this slide. Now if you see this triangle tells you that at the lower level it is important to have collaborations for the engineering as well as the medicine. Engineering means this is like material science, like MSc material science and engineering, and also mechanical engineering, chemical engineering. Now these are like major engineering branches which are under the physical sciences. They are actively involved in this biomaterials research around the globe, and there should be reversible dialogue, or there should be reversible exchange of information or research expertise that should be there to ensure good progress for the science of biomaterials. Now once this collaboration is developed, now these material science people, they will be developing non-living materials. Non-living materials means like synthetic materials like metal, ceramics, polymers. And the medicine people, they have quite good understanding that how different materials can possibly take part in the wound healing process or in the health care of the living materials. Living materials means like patients. Now if these two understanding again they are like fused together, then their interactions actually is important, like how non-living materials when implanted in the patients, how they will interact, and what is the scale of these interactions, what is the material response, like how this material will be developing the neobone or new bone in the implanted region, and what is the host response, like at the implanted region in the animal or in the human being, whether there is any inflammation or not, that is also equally important. Now when the materials will be developed by these material science people or mechanical engineering, certain aspects need to be understood properly, that is structure, composition, function relationship. As I told you earlier, that is the structure property relationship in manufactured and natural materials, these are like important. And from biological aspect like host response and the material response, this interaction like when material is implanted in the human body, that is also important. So if I repeat this particular slide, because this slide is important, so at the basic level, researchers from engineering disciplines like material science and engineering, mechanical engineering, chemical engineering, they should interact and they should collaborate with biological sciences people as well as the medicine people, like clinical trials, like with the medical practitioners or the active researchers in the field of medicine like doctors and so on. So they should be collaborating with each other, and there will be two-way exchange of information, two-way exchange of expertise that is required to totally understand the interactions that I have talked a few minutes ago. Interactions means how a material, non-living material or synthetic material will interact with a living material, that is the human patient. So that's why I have mentioned here at the bottom of the slide. So biomaterials, this particular science essentially combines the concepts of materials and biology. Now how this entire biomaterial science has been developed, now this starts with that fabrication of the materials, and there it requires the engineer, machine people as well as metallurgists, and also ceramics people and polymer scientists for developing the ceramic based or polymer based materials. And then you require a device to design a device, you require a physician or engineer to collaborate, and initially you have to identify a need, like what for this material is to be involved, and for that you require dentist or physician or researcher to answer certain questions. And typically different material testings will facilitate biomaterials researcher, that include mechanical properties, toxicology like genotoxicity, cytotoxicity and so on. biostability, like in the in vivo environment, how this material is stable in biological environment, that also needs to be investigated. Now, before understanding biological response of materials, it is important to know what is the inorganic composition of the human body. For example, if you take the basic elements like oxygen, carbon, hydrogen, nitrogen, oxygen is around 61.4%, carbon is 22.9%. Now, coming to the physiologic elements like calcium and phosphorus, now calcium is around 1.43% and phosphorus is around 1.11%. You have also potassium, which is potassium as well as sulfur. So these are like very small amount, like 0.2%, and some trace elements are there like magnesium and iron, so on. So these are like ppm level. You can see that amount actually is quite small when it comes to magnesium, iron and zinc, because it's in the ppm level. Now, coming to the physicochemical and mechanical conditions in human beings, physicochemical means like pH value. Now, what you see normally here, this pH value also differs depending on the anatomical location of the human body. Like pH is equal to 1 for the gastric content, pH is 4.5 to 6 in the urine, and 7.15 to 3.5 is blood. So all, since the blood pH is 7.15 to 7.35, and that is a pH level that is typically maintained in all in vitro experiments, and that's why it is suggested that pH value of 7.4 is to be maintained. However, you have to note that this pH value that changes, it is not constant throughout the entire human body, and this constant is not true, and this pH value changes depending on what is the anatomical location in the human body that you are considering. Now, coming to the PO2 level, like in the venous and the arterial region, so you have the very high PO2 level, and temperature also it is 30.7 degrees Celsius, because that is the normal core temperature of a human body. But there is a fluctuation in this temperature, like skin at the extremities can go to 0 to 45 degrees Celsius, normal skin it has 28 degrees Celsius. Coming to the mechanical stress conditions in different tissues like cancellous tissues, which are like very porous, this has like stresses can bear maximum up to 0 to 0.4 MPa, so which is extremely low load, and because of the porous nature it cannot take very high load. Now, ligament, tendon, like some of the hard tissues, they can bear the load up to stress up to 40 to 80 MPa, which is relatively high. Stress cycles, which is important for the fatigue properties. So, number of stress cycles, if it is more, then fatigue properties are also much better. Now, typically for walking, if you see 1 to 2 into 10 to the power 6 stress cycles are required for the walking, that when a human being walks, that means this human being actually moving parts of the human body, they experience 1 to 2 into 10 to the power 6 number of cycles. Now, composition of the human blood. Now, blood contains different cells as well as different other elements. Now, different other elements means iron, it is around 0.75 to 1.75 milligram per liter. It has different sodium, potassium and so on. These are like different cations, which is sodium is there for 142 level, chlorine is around 101 mole equivalent per liter, and it has also serum, which is around 61.5%. Total protein in the serum, blood serum, is around 65 to 80 gram per liter, and it has the albumin is 61.5% and globulins is 34.5%. So these are like different proteins which are available in the blood, and fibrinogen is also 4%. Now, blood also contains different cells, as I just mentioned. It is erythrocyte, it is like typically 8 to 9 micron dimensions, and it is like large number of erythrocytes are available up to 10 to the power 6. So this numbers is 10 to the power 6, right? Now, you have the blood platelet, which is there for 10 to the power 5 per microliter, and leukocytes is also 10 to the power 3 per microliter. Now, other things which are important in that, now implant associated tumors, like if you talk about the different metallic solids like titanium 6, aluminum 4, vanadium, number of tumors certain patients were investigated. Now, it has the largest tendency of causing tumors, and these tumors, if they are malignant, then they can cause cancer in the patients. Now, solid cobalt chromoly also, it has large number of tumors that it has experienced, it has caused is 14 per number of tumors they have experienced is 14, cobalt chrome moly microspheres also number of tumors is 15. Now these tumors essentially if they are genotoxic in level, like if they cause the DNA damage, then it cannot be used in a particular implant application. Here again I must emphasize that these Ti6Al4b cobalt chrome moly, these have a very good combination of mechanical properties. However, when they are implanted inside the human body, their wire particles like cobalt or chromium containing or moly containing wire particles, they can potentially cause the genotoxic effect when implanted for the longer duration, and therefore they have also tendency to form large number of tumors, and that is the reason that they need to be replaced with a better materials. So although they have a better mechanical properties, that does not mean they should be accepted for biomaterial applications. This is the illustration of the use of a metal in dental applications, like this is the titanium, which is used widely in the load bearing, like in screws and all in dental applications. Also this is like replacement hard valve. These are like very light, and for that again mechanical properties is not important. And again all the blood cells should not stick over here. So this is the region where the valves can open when you are pumping the heart. So that valves should be very lightweight, and because of this lightweight requirement, many polymeric based materials where density like PTFE, where density is like less than or equal to 1 gram per cc, they should be used. And that is the reason like diamond like carbon coated materials or polytetrafluoroethylene, these are like these should be used. And this should not cause any thrombus formation. Thrombus formation means like blood platelets, they come together, they form a platelets, and these blood cells, so this agglomeration of the blood cells, that should be avoided, and this should be avoided at the maximum extent for any heart valve applications. This is one of the example of the intraocular lens like polymethyl methacrylate and then silicon rubber. Those are the materials, these are typically used for this different intraocular lens applications. Now this is the thing that I was mentioning you a couple of minutes ago. Now this is called stem. Now this stem is typically made of titanium. On this titanium you can put the HAP coating also, like HAP coated titanium also you can use. Now this is the longer part of the structural part or load bearing part of the stem, total hip joint, so hip replacement. And then here you can use some ball, and this ball can be femoral ball, that can be alumina or zirconia. And again at the top here, this is like some polytetrafluoroethylene or ultra high molecular polyethylene. These are like acetabular cup things, and this can be either ultra high molecular polyethylene or high density polyethylene based materials. Now these balls, they will make a small rotating movement here, and they can experience some wear problem also, and these balls will be fitted directly to this femoral stem, which is made of titanium. So this is like one of the most popular examples of where the biomaterials has been successfully used. This is the end of the lecture, and tomorrow we'll start with these other applications, like some of the fundamental properties of the different materials, which you should know before we can realize that how different materials can be successful for different biomedical applications. Thank you.